This is a continuation of the sampling and estimation lecture, and this time we'll talk about other issues involved. Now, as we said in the confidence interval section, that we take the point estimate plus or minus a reliability factor times the standard error, and that reliability factor is from the table. Sometimes call that a critical factor, and that could be a Z or a T. Most of what we're going to be doing involves the T. Now, when you're selecting a sample, you have trade-offs in terms of both statistical and economic factors. Now, it's nice to have a large sample because you increase precision. If you look at the standard error, if you increase n, what happens to the standard error? It decreases. If you increase n, the standard error decreases. That inverse relationship. And so that's attractive because the distribution, the sampling distribution, is going to be narrower. You're going to be more sure of things. Drawback of a large sample includes maybe sampling from more than one population or the increased costs. Now, how can you sample from more than one population? Well, I'll use a time series as an example. Let's say I was looking at a time series of interest rates in the U.S. from 2000 to the present. Well, what's happened? During the financial crisis, you had the Fed intervention, you have the open market operations, interest rates have been kept artificially low. So basically, if I looked at those interest rates over that whole period, I'm mixing basically two different populations. I'm mixing the interest rates that existed without Fed interference and with the interest rates with Fed interference. And that's not the same population, so I'd have to be careful there. If I'm trying to make forecasts of interest rates using the most recent under the Fed intervention would be probably more appropriate to use. And this happens if I'm looking at cross-section of companies. If I take one industry and I expand it to more than one industry, they're not a homogeneous set anymore, and I'm maybe sampling basically from more than one population. So you do have to be careful there. There's also data mining bias. And this is particularly a crucial element because so many people are looking at data mining and all the analytics that we do. People, really, it's the thing, data mine. But if you do that repeatedly, you can overuse the data. And here's one of the things to consider. Let's say that you have a 5% alpha or 95% confidence. If you take 1,000 different variables, 50 of them would be significant at the 5% level. And it's just a matter of the alpha. So you don't want to do something that just doesn't make any sense. If you do a lot of data mining and you try to make financial decisions, it could be problematic. For example, it was the case where one period of time that small firms outperformed large firms. And so people jumped on that bandwagon, they created small cap mutual funds and all the rest. And then it turns out that was just from that one period. And it's just a fluke. It wasn't economically sound rationale for investing in the small cap firms. And so you can end up with a big problem that way. And if you start looking for patterns in data, you get away from economic rationale. And you have to be really careful about that in finance because you usually want to have a reason for something. So that's often we do other tests. We conduct out of sample tests to check this. But with all this data science that's going on, there's a tendency to want to just mine the heck out of data. But you have to sit down and say, why are we doing this? What's it going to show? And is it going to be useful at all? Here's some examples. I could look at length of ticker symbol and return on assets. And I just did this for 2017. And if I take this data, ticker symbols can be 1 to 5 characters. Generally, firms on New York Stock Exchange have 1 to 3. However, that rule is no longer the case. You will find some with 4 on the New York Stock Exchange. Generally, if they have 4, it's going to be on the NASDAQ exchange. 5 means they're NASDAQ and in trouble. So is there a rationale for what we see? No, not really, except for the 5th digit. Okay, if they're in default, they're having financial difficulty, NASDAQ will add a 5th character. Yes, we expect those to have very poor return on assets. But 2017 just happened to be a year where the smaller firms did not do as well as larger firms. The following year changed around. So it was not a pattern that we could have traded on to make money. Then if you look on the right hand side of the screen, here's first letter of company name. And this is the return on assets for 2017 for all those companies, say with a B. They outperform those with an E for first name. It's kind of a fluke. It's a data mining. You get in there and you get so excited, oh, there's this difference. But what will happen is the next year they'll just turn around completely. It won't be that way. This is just a random pop-up that happens. Now, one thing I like to do is always play with the moon phases. And if you had the daily returns on the market, 2017 to 2014, and you look at those with the coding of the moon phase, and there's a coding system that's used, 0 for new moon, 0.5 for full moon, and each day is going to be 0 to 1. Now the question is, why would it work? Why would it not? Well, I can find a positive correlation, a relationship between it, but so we could see that there's a different behavior for different phases of the moon. There's no reason why this would work. Absolutely none. The gravitational pull, all that, none of that would affect stock returns. It has no economic rationale. But if you look hard enough, you mine that data enough, and you can see different returns for different phases of the moon. Sometimes, not always. Now we do have sample selection biases. And so we have to be very, very careful to make sure that we don't have any biases in our sample. For example, survivorship bias. And this is where you can only observe those firms that have succeeded and therefore survive. And the classic example of this is looking at hedge fund performance. Hedge funds don't last very long. I think the average life is somewhere around 6 months. So if I were to go to Bloomberg and log in and look at hedge funds, I might see some fantastic returns for those hedge funds. What I'm not seeing are all the hedge funds that died 3 months ago, 6 months ago, last year, and so forth. It's a survivorship bias. Only those that are going to generate positive returns actually do survive for any length of time. Or if I was doing an industry analysis, if I'm doing an industry analysis, I'd want to look at those firms that existed in the past as well as the firms that exist now. So if I was analyzing the retail industry and I was looking at looking over time, let's say the last 10 years, I would want to include those firms that existed 6 years ago and don't exist now and so forth, because that was part of the industry, part of the competitive landscape. There's also the look-ahead bias, and that's using data that wasn't available, but assuming that it was. And this has to do when you mix market data and accounting data. And the classic example is the PE ratio, although there are many others. Some people form a PE ratio by using fiscal year earnings and end of year stock price. Now remember what a stock price includes: all available information. So at the end of a fiscal year, let's say fiscal year end December 31st, 2018. So on that day, if you pull that price, closing price on December 31st, 2018, that contains all known information about the earnings of the company. But when are the fourth quarter earnings available for that company that make up that fiscal year earnings? They're not going to be available for another 30 days, 45 days. And yet you're using a price that doesn't have that information. So you're mixing things that have different information content. So it's a look-ahead bias. So there are ways to correct for this, and you'll see that some financial services do correct for this, some don't, some do. And this is something to be aware of when you're actually doing some form of financial analysis. There's also the time period bias, and this kind of relates when I was talking about interest rates, or if you talk about regulatory changes, anything. If you talk about an industry that was highly regulated and then they're not deregulated and so forth, or yeah, there's going to be things if you choose a certain time period that may change. So just getting a larger sample, a broader time period may not fix things. It may actually make things worse. So let's take a moment and talk about how you do sampling and simulation in Excel. Now, Excel has built-in functions that you can use to generate random numbers, and you can generate random numbers based on a particular distribution. So say normal distribution. So it has a function rand, and it has rand between. Rand just generates a real number between 0 and 1, and you don't put anything in the brackets. Rand between, you specify the lower and upper bound, but they have to be integers. There are ways to play with this in terms of programming if you need something that's a fraction, but this will tell you how this is how the basic function works. Now these are volatile functions, so if you put these in to a spreadsheet and you refresh the spreadsheet, or you click F9 for example, new numbers are created. So it's volatile, it's different. Every time you open up the worksheet, it'll be a different set of numbers. If you don't want them changing all the time, if you just want to draw a random sample and keep that sample, you'd have to copy and paste to keep in. Otherwise, it'll keep changing every time you refresh the page. So basically, to draw a random sample, an easy way to do this, I could assign each item a number and then do a rand between. So let's say I drew 1,000 companies' stock prices down for the year. Let's say December 31st, I took all the stock prices for all the New York stock exchange firms. Then I would number them 1 to 2,200 or however many there are. Then I would use rand between to randomly draw a number between 1 and 2,200, and then use my reference function to locate information about that company. So a lookup function or a VLOOKUP, for example. So if I define the population as publicly traded U.S. stocks at the end of 2016, and I take a sample stock price, let's say that's 95.12, so that includes New York, American, and NASDAQ, and you assign a number to each one. So each company ticker has a number associated with it. So you would then draw a random number using rand between for this, and then look across to see what the price is. If you want to draw a random sample of 100, and then you draw it, and you do this for 100 cells, and then use VLOOKUP to do it. So you would use VLOOKUP, and it would select the observation and the price. So the observation number, this would be the random number, and then the price. Now creating a sampling distribution, basically what we're going to do is select a sample of a certain size, say 10 or 20 or 15, whatever. Calculate the statistics, say the mean. Do it again, do it again, do it again. So you have repeated number of trials. These are usually called trials. And then you calculate the sample statistics. So for each one, so you'd have a mean, another mean, another mean, and then you'd have the distribution of the means. So if you have 500 samples, 20 observations each, you have a population mean of 3% and a standard deviation of 4%. So what you do is you specify the population mean and the standard deviation, specify the distribution, let's say a normal distribution, and you set up the worksheet. So what's going to happen is your trials are going down different rows, and across here the observations in a given sample. and then you'd use the norm in, and then you'd use rand as the first function, part of the function. This is, rand should be the probability. So by using rand, we're getting a number between 0 and 1, and so that'll be our probability that we're using, and then we'd lock in the mean and standard deviation. So what will happen is you do this all the way across and you get a sample. And then you copy it down. Well, I double click and copy it down. Make short work of that. And then you can use the average, calculate the sample average for each of the samples. So you come over here and calculate the sample mean for these, sample mean for these, and so on. So you end up with 500 sample means when you're done. And then you can say, what's the mean and standard deviation of these sample means? And you can see that the sample mean, the mean of the sample means, is close to the population mean. Now we only drew 500 samples. If we were to do a full simulation of that, we'd want 10,000 or 100,000. The sample standard deviation, you'll notice, is much smaller than the population. This is the standard deviation of the means. So we calculate the standard deviation of the set of means. And it is going to be smaller than that. And it's going to be smaller because you take the standard deviation and you divide it by the square root of n. So we expect the standard error for sample 20 to be around 0.89944. Now every time you hit F9 with this worksheet, if you build it this way, all the numbers change. But if you have a large sample size and a large number of trials, the basic result, the mean of the means and the standard deviation of the means, should be about the same. It's large every time you hit F9. And then what you do is you look at a histogram, which you know how to form, and this will give you the distribution, and you'll see that it looks a lot like what we describe the population distribution to be like. You can do the same thing in SAS, and basically, you know, we're used to using SAS by reading some data and then manipulate the data, but you can actually generate data in SAS. So you can generate random numbers just like you did in Excel. It's actually easier. And so you can generate random numbers actually for more distributions than you can for the Excel. So there's normal, log normal, but there are many other distributions available. And so you can do quite a bit, and you would use a rand function in SAS. And in the rand, you specify the distribution, the mean, and the standard deviation that you're drawing from. And so then you set up a SAS program, and what you're going to do is you're going to, in this case, 10,000 numbers, and I'm going to generate these 10,000 numbers, and then I use proc univariate to actually calculate the means and then a histogram. So I can do this in Excel by working down a spreadsheet, or I can do it in SAS with just a little bit of coding here and a little bit of looping that says, right here I'm doing a normal distribution as well as a uniform distribution. I could have just done the normal, no problem. But what this says is, do it from 1 to 10,000, use the normal distribution to generate a random observation, output, make that data available, and then end this loop, and run means go do it. Then proc univariate says, hey, you've got this variable norm, and then I can analyze it, get the mean and all that, and then do a histogram of it. I can do the same thing for UNIF, which is for the uniform distribution. And then I can do the sample statistics, and you see we're getting something very similar to what we got with the Excel. And here's our histogram of our simulation of 10,000.